Hi, I'm Tom O'Hare, and this is my final project for Artificial Intelligence for Earth Observations. This project investigates whether Sentinel-2 satellite imagery and machine learning methods can be used to detect urban expansion, vegetation change around Ho Chi Minh City in Vietnam between 2018 and 2026. I chose this study area because Ho Chi Minh is one of the fastest growing urban regions in Southeast Asia and is surrounded by environmentally important mangrove ecosystems within the Can Gio coastal region. Mangroves are important because they provide coastal protection, biodiversity support, and carbon storage, while rapid urban growth can place increasing pressure on surrounding ecosystems. Traditional environmental monitoring often requires extensive field surveys, which can be expensive and time consuming over large areas. Remote sensing provides a scalable alternative by allowing environmental change to be monitored using freely available satellite imagery combined with machine learning approaches. This project used Sentinel-2 Level 2A imagery acquired from the Copernicus Data Space ecosystem. Sentinel-2 is a multispectral Earth observation mission operated by the European Space Agency and provides imagery across visible and near-infrared wavelengths at a spatial resolution of approximately 10 meters. For this workflow, I used the blue, green, red, and near-infrared bands from imagery acquired in 2018 and 2026. Dry season imagery was selected to reduce cloud cover and minimize seasonal variability between observations. Two spectral indices were also calculated. The first was the Normalized Difference Vegetation Index, or the NDVI, which highlights vegetation health and density using red and near infrared bands. The second was Normalized Difference Water Index, or NDWI, which highlights river, estuaries, and coastal water bodies. These indices were important because they help interpret land cover patterns prior to machine learning classification. The workflow began by pre-processing Sentinel-2 imagery and calculating NDVI and NDWI. I then applied k-means clustering as an unsupervised baseline classification method. K-mean groups pixels into clusters based purely on spectral similarity without requiring labeled training data. Initially, I attempted to compare independently trained k-means classifications between 2018 and 2026. However, this produced inconsistent temporal classifications because cluster behavior changed between years. This became one of the most important findings in the project because it demonstrated the difficulty of using independently trained unsupervised models for temporal change detection. To improve classification consistency, I then trained a random forest classifier using pseudo-labels derived from the 2018 k-means classification. Random Forest is a supervised ensemble learning algorithm that builds multiple decision trees and combines their predictions. The Random Forest model was then applied consistently to both years, allowing more stable land cover classification and more reliable change detection. Finally, feature important analysis was performed to investigate which Sentinel-2 bands contributed most strongly to the classification results. These figures compare the k-means and random forest classification outputs for both 2018 and 2026. K-means provided a useful exploratory baseline and successfully separated broad spectral regions such as vegetation, water, and urban surfaces. However, because k-means is unsupervised, the clusters were highly sensitive to spectral variability between years, resulting in inconsistent class behavior during temporal comparison. This meant that some apparent changes in the k-means outputs were likely classification inconsistencies rather than genuine environmental change. The random forest classifier produced more stable, interpretable land cover classifications because the same trained model was applied consistently to both years. This highlights an important change in temporal remote sensing workflows where classification consistency is critical for reliable change detection. These figures show the final random forest classification outputs and the change detection map. The random forest classifications show that the water bodies and vegetation remained broadly stable between 2018 and 2026, while urban areas remained concentrated around Ho Chi Minh City. Unlike wildfire remote sensing studies where environmental changes are usually very dramatic, changes within this project are much more subtle. Most detected changes were relatively small and spatially scattered rather than concentrated in large, coherent regions. This highlights the challenges of detecting subtle environmental change using limited spectral inputs and demonstrates the importance of classification consistency in temporal remote sensing workflows. The feature importance analysis showed that near infrared or NIR band contributed most strongly to random forest classification. This is expected because vegetation is strong, spectral response in near infrared wavelength region, allowing effective separation between vegetation, water, and built-up surfaces. I'll now briefly walk through the Google Colab notebook used to implement the workflow and generate the classification outputs. The notebook begins by importing required Python libraries and mounting Google Drive within Google Colab. Sentinel-2 imagery was then loaded using Rastero and spectral bands were downsampled to reduce memory usage because the original Sentinel-2 imagery exceeded available RAM limits during some of the stages of processing. The workflow then generated RGB visualizations alongside NDVI and NDWI outputs to help interpret land cover patterns across the study area. K-means clustering was then applied as an initial unsupervised baseline classification method using blue, green, red, and near-infrared bands. After identifying inconsistencies between independently trained K-means classifications, the notebook then trained a random forest classifier using pseudo-labels derived from the 2018 data. The trained random forest model was applied consistently to both years to improve temporal classification stability. Finally, the notebook generated a change detection map and feature import analysis used in the final results. Although machine learning workflows require computational processing and therefore consume energy, the overall environmental cost of this project remained relatively modest. The Sentinel-2 imagery used in this project consisted of very large raster datasets with image dimensions of approximately 10,000 by 10,000 pixels. As a result, memory management became an important consideration during processing, and image downsampling was introduced to reduce RAM usage and improve computational efficiency within Google Colab. The workflow primarily used K-means clustering and random forest classification, which are relatively lightweight machine learning approaches compared to more computationally intense deep learning models such as convolutional neural networks or vision transformers. Overall, computational advance was therefore likely limited to only tens of watts of electricity usage across the workflow. Despite this computational footprint, satellite-based remote sensing still provides substantial environmental advantages compared to traditional field-based monitoring approaches, because large regions can be analyzed repeatedly without requiring extensive travel, transport, or logistical support. Overall, this project demonstrated how machine learning methods can be combined with Sentinel imagery for environmental monitoring and land cover analysis. While K-means clustering provided a useful exploratory baseline, random forest classification produced more stable interpretable outputs for temporal comparison. The project also highlighted the challenges of detecting subtle environmental change and demonstrated the importance of classifying consistency within temporal remote sensing workflows. Future work could incorporate additional Sentinel-2 spectral bands, ground truth validation data, high-resolution imagery, and deep learning approaches such as convolutional neural networks. Thank you very much for watching.